Welcome to the Foundry, an explainer by Forge College. Today, we're diving into integrating signatures into transactions. We're grabbing all that signature verification theory we've been talking about and using it as an engineering blueprint to build a working, tamper-proof transaction assembly line. So grab your hard hats and let's get building. Here's our quick roadmap for today. We'll start by moving from theory to practice, then meet the transaction envelope. Next, we'll explore the magic of canonicalization, sign the digest, run a tamper test, and finally, lock down some reusable security principles. Section 1. From theory to practice, moving from abstract cryptography to an actual transaction assembly line. In our previous lesson, How Signature Verification Works, we looked at the abstract theory of keys and hashing. But today, we're taking it from the whiteboard straight to the workshop floor. We're going to build a protocol-agnostic workflow right on your local machine using standard SecP256K1 keys. We'll move step by step from generation to final verification. And don't worry, we're keeping this entirely contained in a local sandbox, meaning absolutely zero real funds will be harmed in the making of this explainer. Section 2. Meet the transaction envelope, the package that holds our cryptographic proof. Think about it like this. You can't just hand a loose handful of items to the post office and expect them to magically arrive at a destination. You need a standard box. Before we sign anything, we need a standardized container. Our transaction envelope has three very strict components. First up is the payload. This is the actual action data, like Alice pays Bob. You can think of that as the packing slip. Next is the pub key, a hex string that acts as the sender's verifiable ID. And finally, the signature, which is our 64-byte compact hexwax seal. Section 3. The magic of canonicalization, standardizing the payload before signing. Okay, this right here is arguably the most crucial step of the whole assembly line. Why? Because nothing, and I mean nothing, will ruin your day faster than a single rogue spacebar tap completely destroying your cryptographic proof. I am entirely serious. Enter canonicalization. Think of it like perfectly organizing a messy desk before taking a photograph. Everyone who looks at that desk needs to see the exact same layout. We are standardizing the data, sorting JSON keys alphabetically, stripping out variable white space, and locking down the exact sequence of bytes so both the signer and the verifier compute the exact same digest. If you skip this standardization step, you're in trouble. Two identical messages with slightly different formatting are going to produce completely different hashes. A messy, uncanonicalized payload might have the right information, but shuffled keys and random spaces make its hash wildly unpredictable. But once it's canonicalized, the data is mathematically locked in place. Alphabetically sorted keys, deterministic spacing, no extra white space. That guarantees the verification process won't suddenly fail over a stray, invisible character. Section 4. Signing the digest. Stamping the seal of authenticity. With our raw materials neatly standardized, we can finally press them into a fixed shape and stamp our seal of authenticity. Let's walk through the signer's journey. Now remember this rule. You never sign the raw text. You always sign the fixed size hash of the standardized payload. It's a simple three-step process. Step 1. You canonicalize the payload. Step 2. You hash those bytes using SHA-256 for a deterministic digest. And Step 3. You actually sign that digest. To do this efficiently, we use deterministic ECDSA, specifically RFC 6979. This ensures your signatures are completely repeatable for the same digest and key. It essentially removes all the randomness from the signing process. If you input the same private key and the same payload, you're going to get the exact same mathematical signature every single time. This deterministic behavior is an absolute lifesaver for debugging your code, which is a key concept we emphasize in the Web3 learning programs at Forge College. Section 5. The tamper test, quality control and intentional breakage. All right, our transaction just rolled off the assembly line securely, so let's send it over to quality control. Honestly, you don't really know a system is secure until you see it reject bad input. The verifier's journey repeats the exact same mechanical steps to make sure the final product matches the original blueprint. They receive the envelope, canonicalize the embedded payload using the exact same rules the signer used, recompute the SHA-256 digest, and then verify the signature using the attached public key. If you get a green light, the math holds up. But what's really fascinating is what happens when someone actively tries to cheat the system after that wax seal has been applied. Let's say a bad actor, or maybe even Alice herself, intercepts the transaction envelope and sneakily tries to bump up the payment amount from 42 to 43. What happens then?
Well, altering even a single digit changes the hashed digest entirely, which instantly breaks the cryptographic binding. Because that 42 became a 43, the canonicalized byte sequence changed. Because the bytes changed, the SHA-256 digest completely changed. And because the digest changed, it doesn't match the original signature anymore. The system correctly shouts verification fail and rejects the tamper transaction on the spot.
Now, what if your verification fails when you didn't tamper with it? It happens to the best of us. Before you pull your hair out, run through this quick debugging checklist. First, check for a canonicalization mismatch. Are both sides using the exact same settings or libraries? Second, check for a hashing mismatch. Are your bytes or UTF-8 text encoding perfectly matched before hashing? And third, look for a signature encoding mismatch. Are you confusing a compact hex string with a DER encoded string? Seriously, 9 times out of 10, your bug is hiding in one of these 3 invisible failure points. Section 6. Reusable Security Principles, the Universal Foundation for Transaction Protocols.
By building this simple demo, you have just mastered the exact mechanical principles that secure almost every major decentralized network in the world. This isn't just theory anymore. It is the operational foundation of Web3. These 3 layers combine to form the canonical signing surface. You need agreement on serialization to ensure the identical byte sequence. You need agreement on hashing to compute that deterministic digest. And you need agreement on encoding to parse the signature correctly. Alter any single piece, and the whole verification breaks.
So the ultimate takeaway here is that cryptography relies on absolute byte-for-byte precision. It simply does not care about general human meaning. A computer network doesn't understand the abstract human concept of a payment. It only understands identical bytes and perfectly aligned cryptographic proofs. Signatures protect the rigid deterministic math, not the ambiguous text. Keep this blueprint handy as we move into our next lesson on non-repudiation. But before we wrap up, think about this. Our current setup definitely prevents tampering, right? But what stops someone from taking that perfectly valid Alice pays Bob 42 transaction and just submitting it to the network 100 times? How would you include a timestamp or nonce to prevent those replay attacks? And how would you efficiently represent the signer identity on-chain without sending a massive public key every single time? Think on that. And be sure to visit forge.college to learn more about Web3 security and continue building with us. Thanks for joining me for this explainer.